So this last part of chapter 3 is has to do with more of the statistical um, probabilities of getting genotypes that are in line with Mendel's phenotype. So last week we went over multiple loci crosses, which really looked into genotypes for two different traits. So the question or the problem that we looked most specifically at was taking two homozygous individuals that were homozygous, dominant and recessive, respectively, for round and yellow and then wrinkled and green seeds. And in the F1 generation, it produces 100% of the heterozygotes, and those heterozygotes are then allowed to interbreed or self-fertilize, resulting in an F2 generation with the ratio of 9:3:3:1. So there's these Punnett squares can actually get to be very large, especially if you add in another trait like seed coat color. So there is a simpler way to kind of work through these problems, and that is the expected proportions method. So this does not involve any Punnett squares, but it really just involves looking at individual traits on an individual basis and then multiplying those results together. So for example, if we had two heterozygotes, very similar to our F1 generation, that were produced both round and yellow seeds, and they were allowed to interbreed. What we would do first is treat each one of these traits separately. So we would look at shape first, and then color second. So shape would be 100 or would be the R alleles. So you would have big R, little r from one parent and big R, little r from a second parent. And in that cross, you would end up with a 3-to-1 ratio of round versus wrinkled peas. The second color or the second trait would be color. Very similarly, you would take the heterozygote from one parent, multiply that by the heterozygote from another parent, treat them individually, and you would also get a 3-to-1 ratio of yellow versus green seed colors. So the next step would then be looking at these two traits separately. So we know that in seed shape, we've got round or wrinkled, and that's going to come in as a 3-to-1 ratio, or 3 out of 4, 75% are going to be round, 25% are going to be homozygous wrinkled. In the second column, we can then add in the color, the seed color. So we know that for the round phenotypes, we either have two choices for color, yellow or green. Yellow can be, it doesn't matter what the second allele is, because as long as there's a big Y, that we know that the yellow allele or the yellow color is going to be the phenotype. So what you end up doing here is just multiplying across. So you take your 3/4 of the round individuals, multiply that times 3/4 of the yellow individuals to get a total of 9 out of 16 seeds that are going to be round and yellow. Likewise, you're going to do that again for the rest of the 75% of the seeds that are round, except instead of looking at the yellow seeds, you're going to look at the green seeds, and you just multiply across. So 3/4 from the round seed times 1/4 from the green seed gives you 3/16 that are going to be green. And then you just complete that pattern for the wrinkled phenotype as well. So another example is to look at this heterozygote crossed with a homozygous recessive trait. Again, our first character is going to be seed shape, second character is going to be seed color, and you just multiply across again. So we know that if we treat them individually, 50% of that of the offspring from that cross is going to be round, 50% are going to be wrinkled, and then you just multiply across based on the percentages of the two seed colors that can occur in that second cross. To make this a little more complicated, because we like to do that, if we were to add in a third trait like the seed cover, it would either be gray or white. And what you could do is very similarly just split these up into three major columns. So your first column is going to be the shape of the seed, the second color is going to be the color of the seed, and the third column is going to be the color of the seed coat. And you just multiply straight across, and you end up with some pretty big numbers over here because we have three different genes in this cross. All right, so one other way to predict the percentage of a cross that is used quite often is called the chi-square test, or the goodness of fit test. And this test really tests if what we observed in a certain cross actually fits with what Mendel's laws say it should fit with. So for this example, if we have a dominant recessive relationship where the purple flower is going to be dominant, the white flower is going to be recessive, in that F1 generation, there's 100% of those individuals are going to be purple because purple is dominant. And then in the F2 generation, we actually observed that 105 purple flowers with 45 white flowers. So we can use the goodness of fit test to identify if what we observed was what we expected and falls in line with Mendel's principles. So the way you set this up is in three major steps. The first step is to build a table where you have phenotype, what you observed, and what you expected. In this example, the phenotypes that we were dealing with were a purple flower and a white flower. We observed 105 and 45 of those flowers respectively, totaling 150 total flowers. So now to calculate what we expected, because this was, I'm going to flip back here just a second, because this was a dominant recessive genotype, we know that the observed, or what we expected, should be in a 3-to-1 ratio, because the dominant purple flower should show up 75% of the time, and the recessive white flower should show up 25% of the time. So you take those fractions, multiply them by the total, and that will give you what we expected to happen. The second major step is to use this chi-square formula, where a chi-square is represented by x to the second power, and it represents the sum of the observed minus the expected squared divided by the expected. So you're going to have two terms here, one for purple and one for white. So in our purple example, we observed 105 flowers, but we expected 112. If you take that product, square it, then divide it by 112, you get 0.5, and you're going to run through the same process for the white flowers. So we observed 45 flowers, but we expected 37.5. Run through the math, you get a chi-square value of 1.5 for the white flowers. Then you just total the chi-square values for the purple flowers and the white flowers, and that gives us a product of 2.0. The third step is to identify the degrees of freedom and the probability factors that you're going to be dealing with. So I'm going to show you a table on the next slide, and to use that table efficiently, you have to know the degrees of freedom and the probability cutoff values. So the degrees of freedom is calculated as n minus 1, where n equals the total number of phenotypes possible. So in this example, we had two phenotypes possible, purple and white. We're going to subtract 1 to get a degrees of freedom of 1. And then the second piece of information that you'll need for the table is the probability. So the probability that we're going to determine as significant versus non-significant is if we have a value that is less than 0.05. So we know that our calculated chi-square value from the previous slide was 2.0, and we know that our degrees of freedom were 1. So if we follow this row of values, we find that our chi-square calculated value falls in between 0.5 and 0.1. So which is larger than 0.05, which is our cutoff value. So if we had had a value that was less than 0.05, we would have had a deviation from what we expected. However, since our value was 2.0, it fell in between 0.5 and 0.1. Therefore, we can conclude that there is no difference between the numbers that we observed in the cross versus what we expected. All right, so two more major components to Chapter 3 is this incomplete penetrance concept, and this is where a genotype doesn't always produce an expected phenotype. So polydactylism is where you have extra fingers and toes, and if you get a gene that has or a dominant gene for incomplete penetrance, then you may see a wide range of expressivity. So people may have the gene but don't show the trait. So penetrance has a mathematical definition and is defined as the percentage of individuals that have a particular genotype that express the expected phenotype. So we can actually calculate the percentage penetrance. So one way to do this is, like in this example here, if we have 42 people that have an allele for polydactylism, but we only found that 38 of them were polydactous, so actually showed the trait, then we would divide 42 by 38 and we would get 90% penetrance. And finally, the last concept of Chapter 3 is expressivity, and this is the degree to which a character is actually expressed. So still using the example of polydactylism, you could actually see a large variance in how severe that trait is expressed. Some people may have full digits or full extra digits, so extra fingers and toes that are functional, and other people may have just little tags of skin on their foot. So the degree at which those traits are expressed can vary depending on how highly expressed they are. All right, so that's the end of Chapter 3. There is a chi-square example on the end of this lecture if you guys want to look at